industry and agents for a lot of the training videos that he puts together. So I'm really looking forward to his talk here. Again, talking about moving past the routine. So without further ado, Josh, I'll let you go ahead.
Thanks. Can everyone hear me? Is the microphone on? Maybe, maybe not. I'll talk loud. I noticed with Dr. Grove, the mic was going in and out, in and out. Putting it up higher. Now you'll get my beard scratching it.
Okay.
All right. How's that? Better, worse? Doesn't matter. Okay. So yeah, I noticed that as Dr. Grove was going, it was going in and out on technical difficulties. I'm pretty loud though, so I'll use my outdoor voice. How's that? It's always a risk being on the same program as Dr. Grove because we like to have healthy debate about soil fertility and nutrient management. Is Grove still in the room? Good. I can say whatever I want about him and disagree with everything he presented to you before. I also noticed they gave him 45 minutes and I got 30 minutes. Like, I'll give you twice as much information in half the time though, so I talk really fast. So I want to talk a little bit about precision management. It's not something that I typically see as much with alfalfa and forage production, but I know that there are some people at least doing grid sampling and some things like that Dr. Grove mentioned. So I'll get into a little bit about that. But first, some of the basics, which Dr. Grove did. Can you guys hear me all right? Yeah. So Dr. Grove got into some of the basics, covered it pretty well, but just to kind of make sure we're on the same page and to correct anything he said that was wrong, I'm going to go over it again. So soil testing is basically made up of 4 different parts. When we think about soil testing, soil sampling, collecting that sample, analyzing it, so getting those results back from the lab, interpreting the results, and making the recommendations. Traditionally, soil sampling is what we always preached as the limiting factor, making sure that that sample adequately represented the area that we wanted fertilizer recommendations for. Making sure that you got enough cores per sample because it's a composite sample of multiple cores, making sure those cores were taken to the right depth at the right time of year. But as we move into precision nutrient management, we're going to talk about trying to split that field up into smaller parts either through grid sampling or zone sampling, and that's what I'm going to spend a bit of time talking about. We're pretty good at soil analysis. I'm going to touch on that briefly, what happens at the lab with your samples and why that matters to you. But then on that last part, interpretation of results and the recommendations we make. As far as precision ag goes, particularly for phosphorus and potassium, we have a long way to go. So I'm going to tell you some of the limitations of a precision strategy based on what we know and don't know as far as interpreting results for that precision setting. So in traditional soil sampling, this is just the basics. You're trying to zigzag, cover that area of the field. Break the field up based on known patterns with the field maybe. They say, 10 to 20 acres per sample. So split that field up into units that are 10 or 20 acres. Our recommendations say 10 or 12 soil cores per sample. And it's funny, I was talking about this the other day out at Princeton, and actually the science doesn't support that. Any guess how many soil cores per composite sample that goes off the lab? So you got your soil probe. How many times should you stick it in the ground, put it in the bucket, and mix to get a good sample? 20. The science basically says you're going to converge on the mean somewhere around 20 to 25 cores per sample. And this is just an example that extension specialists are pretty chicken, and we don't want to tell you to go take 20 cores because they know everyone's going to grumble. So we kind of downgrade it to make you happier with us so we can stay for lunch. So that's basic soil sampling. The last part here, draw a map and keep good records. The most important thing that you can do regarding soil tests and nutrient management is the records you keep. Our recommendations are averages for the state. Every field has a different nutrient requirement. So having a record of what you applied and what the soil test was over time is the most important thing to track trends. How does your field specifically respond to potassium and phosphorus and lime application over time? That's the most important part of a nutrient management plan, is that long-term record. So as far as soil sampling for precision ag, there's basically 2 processes that we use. Grid sampling, I would say, is most common. It probably covers 80 to 90% of precision ag nutrient management. And there's 2 types of grid sampling, grid point or grid cell, and by far grid point is the most common because most of the soil testing that we see is done by an outside, not the farmer per se, but you're contracting that work out. And even if you're doing it yourself, grid point is pretty automated. You take a software program and you lay a grid. Typically, the standard has been 2.5 acres, 1 hectare. And at each intersection of that grid, you go out and take a sample. So at each one of those intersections, you would take 10 soil cores, throw it in the bucket, mix it up, grab a subsample, and that goes off to the lab at each one of those points. So that's grid point sampling. We do see some grid cell sampling, so you lay out that 2.5 acre cell, and then you zigzag across it like it's a little field, and you get a composite that covers that whole area. But grid point is much easier because it doesn't require the user to know anything about the field. You just lay the grid down and go out and hit those points to get the samples. Grid sampling is good at finding human-induced variation in the field, right? Because what are we trying to find? We're trying to find variability in nutrient requirement across that field. We're trying to map that. And just dropping a grid on the field, you can find things that you didn't know were there that were human-induced. Not natural variation per se, but human-induced. An old animal lot, right? Where the old farmyard used to be, but it's been combined into a larger field. Old tobacco patch that was fertilized different. These sorts of human-induced things that we didn't know were there because it's a new field to us, we can find with grid sampling. Directed sampling or zone management is what I think we should be doing. I'm going to talk about some of the weaknesses of grid sampling here in a second. But directed sampling breaks the field up into zones based on typically natural variation, soil texture, topography. We like to use yield maps, and again, most of the work I do in precision ag is related to grain crops where we are running yield monitors and so forth. I personally, if you're in the grain sector and you're doing precision ag, doing zones based on yield I think is a bad idea. I think you should be using your yield zones to test the zones that you develop for soil sampling. But yield responds to nutrients. And so it becomes circular if you use it to control where you put your nutrients, right? Because you can have a low-yielding area of the field because it needs more phosphorus, right? And so, you say, okay, well, this is low-yielding, I'm going to add more phosphorus. Or it may just be low-yielding because of soil depth, and so therefore it needs less phosphorus because the yield potential is lower, right? And so it becomes circular, so I don't use yield to dictate zones. I use physical features that control nutrient availability, rooting depth, drainage, soil texture, slope and aspect, these sorts of things. And we'll get into that in a second. When we talk about grid sampling, what we're doing, if we look at this example here, you're going out on that 2.5 acre grid and you're collecting a sample and getting a known value. And you're trying to predict the value at an unknown point in between. We interpolate. So if you've ever done any grid sampling, you get that map back, that heat map where you have the colors that transition between the grid points. The way we predict those values is through interpolation, which is just a statistical procedure. And it doesn't matter whether you use Kriging or inverse distance weighting, it doesn't matter. It's all just as wrong. So I used to teach grid sampling and interpolation. I used to do this in extension programming and say this is a good idea because I read an extension fact sheet that said this is a good idea, and I read some research that said this is a good idea. And we don't have enough time to get into why it's a bad idea, but it's a bad idea. Because soil properties vary a very large amount in small distances. It's called a stochastic variation, all right? So on average, we can predict it. On average, we do a good job. But point to point, we do a really bad job. And so in this example, I've kind of thrown some numbers in here. 9, 15, 13, 45. In fields, we get these flyers. We get these single points that are really high or really low. And when you do inverse distance weighting or Kriging or any other interpolation, you're using the samples closest to that unknown point. They get a larger weight in the average. So traditionally in the old days, you would have zigzagged across this field, put all the cores in the bucket, mixed them up, and gotten an average for that field. But now we're going to interpolate, and this one flyer that's close by is going to carry the day. And it's going to create an unrealistically high estimation, in this case, of that unknown value. It turns out that 95% of the time, if you do grid sampling or Kriging, the field average gives you a better estimate of that unknown point than Kriging or interpolation by any method. So I'm going to repeat that. the field average will be closer to that unknown value than what your software predicts because of the way soil properties change. So there's a good paper. I can provide you with copies of it. The reference is here, and it's also in your handouts. It's actually a pretty easy to read paper, and this was the first one that I saw that kind of really identified this problem with grid sampling in agriculture. And so basically what that figure shows on the horizontal axis is separation distance, how far apart the points are. 100 meters is 2.5 acre grid. 30 meters is a 1/4 acre, okay, roughly. To use interpolation, for it to work, your R value, which is just a statistical, it's the correlation factor, has to be at least 0.3. You do not hit 0.3 until your grid hits 1/4, more often 1/10 of an acre. That is impractical and not cost efficient. So you're better off averaging your grid data as a flat rate across the field instead of interpolating it. So I had a friend up at Penn State that did that. We're reproducing this in Kentucky as well. We can go in, take a 1/10 acre grid sample, drop out all the points except for the 1 acre. 1 acre grid, that's pretty intensive. And then we can take that, interpolate it, that estimated value for this point we didn't sample, but we actually did sample it. And we take the interpolated value and compare it to the actual value that we measured, and we take the field average, and 95% of the time the field average is closer than what the interpolation predicted. So I'm just hammering home the point. Interpolation in soils, if you're taking your sample coarser than a 1/4 acre, doesn't work. Now, you say, why have we done it so long? Why hasn't anyone told us this is wrong? It doesn't necessarily hurt you. Soil test values, because it's up against a hard number on the left of 0. You can't be lower than 0. Skew right. So that means if I go out and grid sample, I'm going to get this distribution of samples that skews right, high. So when I take a grid map and interpolate it, I tend to cut my fertilizer rate. It's a mathematical function. It's not real. Because it skews right, because you're up hard against this wall on the left-hand side, by luck, it always cuts your fertilizer rate. And as I'm going to talk about in a second, our recommendations, and as Dr. Grove pointed out, have fat built into them. In other words, all our recommendations are above the yield maximizing rate. And so what you've done is you've done variable rate. It's always going to cut rate just because of mathematics, not agronomy. But you're varying it above the true requirement. So you're not going to lose yield. So you cut rate, you didn't lose yield. You could just do a field average of your grid because it's a better estimation, or you could just take our recommendations and cut 20% off. You'd get the same outcome. It doesn't hurt you, it's just not right. And this is because of accuracy versus precision, right? So I always give this example. We have a faculty member in my department that teaches statistics, and he has to hang up cartoons to recruit students to take his statistics class. I don't know why. I thought statistics sold themselves, but apparently kids don't think it's fun anymore. And it's this cartoon. It has 3 frames, and he's relabeled it. In the first frame, there's these 3 people that are deer hunting. There's a deer downrange, and the first person on the left he labels as the soil scientist. It wasn't me. It was Dr. Grove. He misses a yard to the left. That's why it was Grove, not me. Misses a yard to the left. In the second frame, the plant scientist on the right misses a yard to the right. And in the third frame, the statistician jumps up and goes, got him. On average, they killed the deer. They never hit it, right? And that's what our fertility recommendations do. They're accurate. People always say, I wish the university recommendations were more accurate. We need more accurate fertilizer recommendations. Our recommendations are very accurate. If I knew the true requirement of your field every year for 10 years, the average of those numbers would be what we recommend. In every single year, what we recommend is wrong. So this goes back to the need to have those records so you can understand how your field responds to those fertilizer inputs. That's the most important part. And this also gets at why interpolation doesn't work for soils. Interpolation gives you an average that changes based on the samples closest to that point you sampled, but in the field there's actually extreme variability. So we need a better way if we're going to do subfield management, and I think it gets into doing zones, but the problem is zones are difficult, particularly if someone from outside the farm, a consultant, a retailer, an ag service provider is doing the work, because it requires being engaged in the decision-making process for every single field individually. With grid sampling, I can take millions of acres, put them in the computer, and push the grid button. There's no easy button for zone sampling. Briefly about soil analysis, and this gets into that precision management about why there's uncertainty around doing precision nutrient management. So when we do soil testing, we're looking at this stored pool of nutrients. So on the left-hand side, you've got soil minerals, organic matter, and exchangeable nutrients, or nutrients that are in the soil, on the soil colloids that can easily go into solution. Plants can only take nutrients up out of the soil solution, right? And so you have this short-term to long-term storage, and soil testing really tries to provide an index of these different pools. Malic-3 phosphorus isn't total P, it's not plant available P, it's just phosphorus that is extracted by a strong acid with EDTA. It's grabbing phosphorus or potassium out of these pools in the soil that are part long-term and part short-term, and the buffer capacity is really important. Buffer capacity is when the plant takes up nutrients, there's this big reserve like an iceberg that's in the background that backfills the plant available pool, okay? And so when we do soil testing, you know, there's a lot of factors that impact this quantity versus intensity relationship. Intensity is what the plant gets. Quantity is the supply in the background. And since there's so many factors, soil testing really just provides a relative index. So for phosphorus, the critical level that University of Kentucky has determined is somewhere around 30 pounds per acre of phosphorus, 35 pounds per acre of phosphorus. And that's just kind of a relative index. In my opinion, I'd like to get rid of the units on soil testing and take, for phosphorus, 35, set it equal to 100, and say for every nutrient when you hit an index value of 100, you don't need to fertilize anymore, because it would make it so I don't have to remember numbers, and I'm bad at remembering numbers. But it's just an index of relative availability. And there's a lot of different soil tests out there, and it doesn't really matter which one you use, because what matters is that you have local correlation and calibration that Dr. Grove discussed, and I will again here in a second in the context of precision management. But those soil tests are just grabbing little slices out of the pie in the total amount in the soil. You've got organic phosphorus, clay phosphorus, iron phosphorus, aluminum phosphorus, calcium-bound phosphorus, and whatever extract, you know, Bray P, up in the tri-state fertility guidelines, Ohio, Indiana, Michigan, they're actually getting ready to switch over to Malic-3 with their new release. In Tennessee, they use Malic-1 still. The rest of the free world uses Malic-3. In Tennessee, they're just a little bit behind. And so, you know, it doesn't matter what soil test you use. You just have to have that local correlation and calibration to drive the interpretation of the results. So correlation is, as Dr. Grove pointed out, that relative yield versus soil test. And so we try and find that point above which on the soil test scale that we don't need to add any more fertilizer. Okay, so that's correlation. Calibration is how much fertilizer do I need. So now I go out to multiple sites with different soil tests. So in this example, the gray one, soil test 10, orange soil test 20, blue is soil test 30. This isn't real data. This is idealized. Field research never looks this good. I tell young extension specialists, don't let real data get in the way of a good story. You know, if I showed you real calibration data, you'd be like, man, there's no point in even fertilizing. But with calibration, I'm trying to see where I maximize yields on the fertilizer rate based on a specific soil test. So I need more fertilizer to lower my soil test, but I can still get to the same yield point. So this gets after that point that Dr. Grove made adequately, was building up soil tests isn't necessarily the best way to go, because I can maximize yield with a much lower rate. And if I have really low soil tests, it's hard to build. Now, with crops like alfalfa, you do have a big removal rate, and so that's built in our recommendations, but the recommendation is predicated on kind of your philosophy. And so as Grove says, there's kind of these three different main approaches: sufficiency approach, which is just apply what the crop needs. But we don't know what that number is because that data was lost to history. Back in the old days when we were doing field calibrations, we didn't keep data stored on computers. A lot of this work was done with hard copies, and we just weren't as careful with the data. The university made recommendations, but the data behind it we didn't archive efficiently. I think that's unfortunate, because my personal philosophy is at this point, most people aren't explicitly using university guidelines. They're getting information from a lot of sources. Fertilizer dealers, retailers, consultants. And I really think the university's position should be to put the data out there of the actual calibration and let you hold the recommendations you're getting up against that calibration data. And then make your own decision, you know? So the sufficiency approach requires knowing what that sufficiency recommendation is, but we don't necessarily have that data. We just have our total recommendation. The build and maintain is what everyone uses, some sort of hybrid between the build and maintain and sufficiency. The build and maintain would have a really high build rate at the low end, as you can see with that blue line, and then have a maintenance rate of always crop removal going out. We use a hybrid. Our hybrid approach is lower than some of the private sectors. I just put a note on there of base cation saturation ratio. This is the idea that there's an ideal soil and you need to balance calcium to magnesium to potassium in the soil. It is complete poppycock. There is no scientific evidence for it, and the people who invented it, they're some of the main protagonists of it in the scientific community. Came out of the 20s and 30s in Rutgers and then went to Missouri and Auburn and some places like that. But the people that established it, the professors that developed it, actually retracted their statements towards the end of the career and said, we were wrong, but the private sector never let go of it. So with a sufficiency approach, we kind of have this low rate of fertilizer versus, soil tests. But with our recommendations, and I apologize, this slide here I just made up for corn, but it's same shape for any product. This is our Kentucky recommendation. So you can see, sufficiency is somewhere down in here. I don't know exactly what it is, but this is my guess for phosphorus of what it would look like. And then we have a build component for really low soil tests. We get closer to the sufficiency, but with a little extra insurance on there. And then we have this maintenance out past where we don't think there's a response. So around 30-ish soil test, which is 15 in milligrams per kilogram, what I show here. And we go to this kind of maintenance. We don't think you're going to respond to phosphorus, but we add some there as insurance. So I think our recommendations are too high at the university. How many people in the room think our recommendations are too high? That's what I thought. But most of the data indicates our recommendations are above the yield maximizing rate. It's not too high from a philosophical standpoint if you feel you need to build. So that's why I say you're not wrong if you add more than we recommend. You just believe in building more than we do. Our yield maximizing rates are much below the recommendations that we make in general. And this is why we don't put as much in the build component. As Dr. Grove said, this is the data from Tom and Dollarhide that shows soil test change per unit of phosphorus added. And you see that at the very low soil test of less than 5 pounds per acre P2O5, with low soil tests, you get 10 to 25 pounds of P2O5 to change soil test of 1. So down here below 5, you need 10 to 25 pounds for 1 unit soil test change. And then if you get up towards the optimum, 5 pounds of fertilizer is going to change 1. It's nonlinear. And so if you're really low, you're going to be investing a lot of money to build your soil test. I took Tom's data and ran it out here. You can see in the blue line that if your soil test is below 6 pounds per acre, it would take 200 to 600 pounds of P2O5 to move soil tests 10 pounds per acre per year. So if you're down here in this single digit, you'd have to apply 600 pounds of P2O5 just to move 10 points on the soil test scale in 1 year. So that's a lot of investment for little yield. So this was, the question was, what was the pH when this research was done? This was Bill Tom's data on soil test change. I'd have to go back and look at the paper. I'm going to assume that he had the pH at a standard range. But this relationship is kind of, pH is irrelevant. Because as pH goes down, soil test P goes down, right? So one of the things you can do is if you lime, malic-free extractable P will go up. That's part of the story here, is that if you lime, soil P would go up. But this relationship, this nonlinear curve, it doesn't really matter what soil test is. It still takes extreme rates per unit change at the low end. So for precision ag, to bring it back into that question of precision ag, it would make sense to be closer to sufficiency rates. Because remember I said the reason why precision ag's kind of worked is because we're applying way more than we need, and we're moving around up and down based on these grid samples. But it's above, we have this build component built in. I think for precision ag to work, It's annual fertilizer recommendations, annual fertilizer applications, annual soil testing, and moving closer to the sufficiency rate. I say that knowing that we don't have a sufficiency recommendation, and no one does. If you look at the correlation and calibration data behind university soil tests, where the critical level is and how much fertilizer you need, that's the same data that the private sector uses. No private lab did correlations on Malic 3 to find the critical level. That all came out of the universities. Starting with Dr. Malic in the 80s at North Carolina State, and then moving westward and northward. And so all that data is the same. The rest of it is philosophy. And so I think a precision philosophy, you have to move towards a tighter recommendation that's closer to yield maximizing, because you should be trying to match precisely nutrient application to nutrient need. I don't know what the sufficiency is, but I know it's below our rates. A friend of mine in the industry said, well, maybe since you don't know the sufficiency, and this is the fertilizer industry, you should just use crop removal. So do your soil tests and then have some sort of crop removal factor for a precision application. And I'm not sure that he's wrong. This doesn't help you if you aren't doing yield monitoring on your alfalfa removal, but you have an idea of what you're taking off. Because generally, crop removal is below our recommendation, but above the sufficiency rate. So it's kind of a halfway of getting at what you need to know to do a precision application. But the end of the story is when you talk about precision, this is what we're looking at. This is that buffer capacity, and why in a second I'm going to show you some removal rates versus our recommendations in alfalfa. When I do a Malic 3 test, this is what I see. It's like pH, and this is why precision lime management works. Soil testing for lime, we get pH, which is the active acidity, and we get a buffer pH number, right? We use the Socorro buffer in Kentucky. And the buffer pH is measuring this, which you don't see under the line. We don't have that for phosphorus or potassium yet. The Australians tried to do a buffer phosphorus number. It hasn't worked very well. But there's this component that's that stored component of phosphorus and potassium in the background that when the crop removes some P and K, the soil floats. It's like that iceberg floating up. It has a huge reserve to supply that buffer capacity, and it's trying to reach an equilibrium. So it contributes, the soil contributes some nutrients from that reserve capacity. We just don't know how much that is, except for with pH we do, because we do a buffer test. So last kind of point with forage is when we look at removal and recommendation, what I've got over here on the left side is crop removal for fescue at 3 tons per acre, alfalfa at 6 tons per acre. I just used textbook numbers. I tried to go kind of high. I don't know if that's high or low. I'm not a forage guy, but I thought 6 tons per acre alfalfas would make you pretty happy. Is that right? Yeah. So that's pretty big removal at 6 tons per acre, and look at that K2O number. And Dr. Grove mentioned this. Now look at phosphorus. The difference between a fescue 3 ton per acre crop and alfalfa 6 tons per acre isn't much difference. I've spent most of my career studying phosphorus. It's an interesting nutrient. It's a macronutrient. We think of things N, P, and K. But phosphorus, you don't take up any more phosphorus than you do sulfur. Also a macronutrient, but a secondary. Phosphorus is a very low removal. The reason we consider it a primary macro is because it's hard for the crop to get it out of the soil. But you have very low kind of removal of phosphorus, high removal of K2O. One of the things that I run into with hay production, a lot of people, 300 pounds of triple 18. That's all they apply. And so look at those removal numbers and look at that 300 pounds of triple 18 and imagine doing that for 20 years. Your soil test K is going to plummet, and your soil test phosphorus is probably going to go up because you probably have a lower yielding crop. And that's what we see. When I look at all the hay soil test samples that run through the Kentucky lab, soil test phosphorus is through the roof, soil test K is in the basement. So that's my first take-home point. I know this is a precision talk, and that's very conventional, but 300 pounds of triple 18 is a terrible practice if you're removing biomass from a field because you're removing a bunch of K. So it doesn't make sense to apply the same amount of K and the same amount of P. Then the second thing is here, if your soil tests low, this is what UK recommends. Nitrogen for biomass, this is grass over here on the left. The orange one, again, is phosphorus. The gray one's K2O. So those are our recommendations. And then on the one next to it, if your soil tests low, the alfalfa grass mixture, look at how much K we're recommending. That's because you're removing so much K, and look at your removal line. So we have a removal and a little build component in our recommendations for K. Then you get over to cool season grasses that test medium. And again, our recommendations start to drop way back, particularly for phosphorus. And the reason that phosphorus number drops way back when you touch medium is because now we're going to rely on that soil buffer capacity to supply the phosphorus. But again, we still have a big removal component for the alfalfa in the K. And so that's how our recommendations are built. We have this removal component, a little bit to build in the low, and then if you look at the medium soil test, we have the removal replacement, but we don't have that kind of buffer capacity build component because you're in that medium range. 5 minutes. All right. And so, that removal is basically just the cost of doing business. So, you can run out whatever numbers, but this is the way you're looking at it. The cost of doing business, the price per pound of nitrogen. A lot of folks talk to me about the price of DAP, the price of MAP. If you can find triple superphosphate, potassium sulfate versus potassium chloride is a question I get all the time. That one never pencils out, all right? Because potassium is always going to be cheaper with potassium chloride. And it comes down to price per pound of nutrient and what your recommendation is. And I really also recommend doing this kind of analysis. 1, keep records. 2, look at the analysis of how you apply nutrients. And what's that cost of doing business? You have your nutrients that are removed. You have the nutrients, what your nutrient costs, so you can use that to get the cost. And, so fescue at 3 tons per acre, generally you're removing about 100 pounds per acre of nutrients. And you can hold that up against your fertilizer bill and know what your return on investment in fertilizer is. In summary, grid sampling. I know I've been very harsh on grid sampling, and I recognize that people in the room have done grid sampling. Your data is good. It's the interpolation that is worthless. And I mean that. It's absolutely worthless. But the data is good. So what does that data give you? If you leave the points on the map and don't fill in between like this map shows, you can look at distribution of soil tests. You look for high or low areas where that old tobacco patch was, right? You can look at the median value and the standard deviation. A lot of easy statistics with Excel to understand if you have a field that's very variable or pretty flat in nutrient requirement. So we can look at that grid data. We can even use it to build our zones. Just don't push the easy button on the computer and interpolate. Zone sampling. We don't have good recommendations, but it makes sense to follow natural features. Again, you need to know something about the field and know if that old animal lot is buried in that field somewhere, because that's got to be pulled out as a zone. But we know that soil nutrients, as far as soil test values and requirement, track with topography. Side slopes, the soil is shallower, more coarse textured, more acidic, shallower rooting depth. On the top, it falls somewhere in between the tops and the bottom. The toe slope is where your deepest, richest soils are. So just a basic zone would follow topography. I use yield to test the zone. I don't use it to make the zone. We are working, we've got funding from the Small Grain Growers Association to build these videos out that are going to be short 5-minute videos using free software that will walk you through click by click how to build a soil testing zone in your field. And if we get enough funding, we'll buy licenses to all the software packages that we can afford to try and show, because I know not many people are using these free software packages, but we use them because we know what they're doing in the background, and because I can share them with different farmers, you can just download them. But we also are hoping to get licenses for some of the more common ag programs to be able to show step by step how to use the software to build zones based on topography. But even with a really good map, whether it's a grid or a zone map, we still need to be working on developing what is that sufficiency recommendation, improving these recommendation systems. And I think the only way to do that right now is to kind of use your technology on a site-specific basis. If you're doing precision ag, the biggest advantage you have is the ability to vary rate. So if you have a strategy of doing zone rate, do a couple flat strips across the field and see how they perform, high, low, medium, and see if the recommendation from your private sector consultant or from the university is hitting the mark. Take their recommendation and put some strips out there 20% higher and 20% lower and see what happens. That's the advantage that precision technology gives us. So with that, do I have time for questions, Ray? Couple of questions. Any questions?